So now let's discuss two-way ANOVA. This is a situation when we have not just one factor, but we consider two factors. Both can affect the response. So we have A factor and B factor. And A factor has K levels and B factor has L levels. So this is not I, but small l. And so A1, A2, AK are so levels of the A factor, and B1, B2, BL are levels of the B factor. And for each combination, AI, BJ, we have the response value. In practice, and so we can also present our observations in the form of a table, similar to the table we have already seen. So where the rows correspond to the levels of the A factor and the columns correspond to the levels of the B factor. And in practice, what is inside this table are not just single values of the response, but mean values. So in practice, you usually have a series of measurements of the response for each combination of AI, BJ, and then you calculate sample mean for this sample, and what you see in the table is the mean value. But let's assume that these are just response values, just for simplicity of our mathematical model. So let's assume that Xij is the response level such that A equals AI and B equals BJ. So what is the mathematical model of observations in this case? Here it's almost the same, but the influence of two factors are added. So we still have the response value, we still have the global mean value of the response, and gamma I is influence of the A factor, and tau j is the influence of the B factor, and epsilon aj is the influence of all the rest. So, and usually we know that one of these factors, either A factor or the B factor, one of the factors has some effect. So we know that one of the factors affects the response somehow, and we want to test a hypothesis that the other one also has some effect. So, and we have three cases that are identical to the cases we have considered for the one-way ANOVA. So the first one is the Fisher's test for the normally distributed response. Here we can say that we assume that epsilons follow normal distribution with zero means, and that epsilons are independent random variables. So what do? We calculate sample means, so mean values for rows and tables, rows and columns of our table. So x bar I dot is the sample mean for the ith row, and x bar dot j is the sample mean for the jth column. And we calculate the global sample mean also, as in previous case. And then we calculate sum of squares. So SS is for the sum of squares, and we have sum of squares for rows, sum of squares for columns, and total sum of square that are calculated with the formulas you see now. So these formulas shows us variation between the rows, variation between the columns, and total variation between the variation within the united sample. And then we find the residual sum of squares. The residual sum of squares is total sum of squares minus sum of squares for the rows minus sum of squares for the columns. And after all these auxiliary statistics are found, we can test a hypothesis. We can either test a hypothesis that a factor has no effect against an alternative that a factor has some effect. The test statistic for this test is L minus 1 times SS rho divided by the residual SS. And if the null hypothesis is true, then the test statistic follows Fisher distribution with number of degrees of freedom k minus 1 and k minus 1 times L minus 1. Or we can test a hypothesis that B factor has no effect against an alternative that it has some effect. And so all is symmetrical. The test statistic for this test is k minus 1 times SS column divided by the residual SS. And the distribution of this test statistic under the null hypothesis is Fisher distribution with L minus 1 times k minus 1 times, so number of degrees of freedom is L minus 1 and k minus 1 times L minus 1. So you can just test a hypothesis that A factor has no effect, assuming that B factor has some effect, or you can test a hypothesis that B factor has no effect, assuming that A factor has some effect. So this is what is usually done when the distribution of the response is assumed to be normal, and there is a traditional form of collecting all the auxiliary data in the form of a table. So while solving the two-way ANOVA problem for normal case using the Fisher's test, you usually fill the ANOVA table. I'll show you the table now, and abbreviations that are used there are DF is for degrees of freedom, SS is for sum of squares, MS is for the mean square, F score means the test statistic of the Fisher's test, so these FA and FB, and F critical is the quantile, so quantile that separates the acceptance region from the critical region. So, and this is the table. So we say that we consider several sources, rows, columns, errors, and total. And so for each source, we know number of degrees of freedom, that is k minus 1 for rows, L minus 1 for columns, k minus 1 times L minus 1 for errors, and k minus 1 plus L minus 1 minus their multiplication for the total. Then we have sums of squares that are found according to the formulas I have already shown: SS row, SS column, SS residual, and SS total. Then we have mean squares. So this is like mean squares of marginal means for different rows, for mean square of marginal means for different columns, and the total, sum of squares of all observations. So the test statistic is FA and FB when we test a hypothesis of no effect for A factor and the B factor respectively. And so the F critical is a quantile of a given level. so of the quantile of the Fisher's distribution. Okay, so then instead of Kruskal-Wallis test for one-way ANOVA, for two-way ANOVA we have Friedman's test when we don't assume normal distribution for our observations, and we test the same hypothesis as the Fisher's test. So this is also a rank test, one of the rank methods. But here we rank not the united sample, but we rank each row of the table or each column. So it depends on hypothesis on what factor you are going to test. Now let's assume that we are testing hypothesis that B factor has no effect. So in this case, each row of the table is ranked. So observations in each row are ranked from 1 to L, and small rij is the rank of xij within the ith row. Then you calculate, then you do almost the same as in Kruskal-Wallis test. So you calculate the mean ranks for all columns of the table, and then the test statistic shows us variation between these mean ranks for different columns, for different values of the B factor. And so if the variation is big enough, then this is in favor of the alternative hypothesis, and so we also have right-tailed critical region. And as in Kruskal-Wallis test, here the test statistic also follows chi-square distribution. Chi-square distribution with L-1 degrees of freedom. And when we want to test a hypothesis that the factor has directional effect in two-way ANOVA, we use Page's test. So the null hypothesis is that B factor has no effect. The alternative one is that B factor has directional effect. And so what do? We also rank each row of the table as in Friedman's test. So Rij is the rank of Xij within the ith row. So this is absolutely the same as in previous test. But then we calculate not the mean ranks for different levels of B factor for different columns of the table, but we calculate sums of ranks. So R dot J is sum of ranks that are in the jth column of the table, and the test statistic is sum for j from 1 to L, j times R dot j. So sum of ranks for the jth column is multiplied by the column's number. And then Page proved that the test statistic, that L, is also asymptotically normal. So for big sample sizes, it follows normal distribution. And then we are to standardize this statistic. So we calculate the expected value and the variance according to the given formulas that were derived by Page. And then we standardize the test statistic, and L tilde is L minus E of L divided by the square root of the variance of L. So, and then we test a hypothesis assuming normal distribution. So this test, sometimes it is called Page's test, sometimes it is called Page's L test, as L is the standard notation for the test statistic in this test. And sometimes it is called Page's trend test, the same as for one-way ANOVA. We have John Kear's trend test, and here we have Page's trend test. As we suppose that we are looking for a trend here, like we say that not just average values of the response are different for different factor levels, but that there is a trend. So when the number of the factor level increases, the average response is also increasing. So, and as we assume the standard normal distribution for L tilde, so then we use the quantiles of the standard normal distribution to separate the acceptance and the critical regions.